Hello, everybody, and welcome to MEERTALK. My name is Kaeza Fern, and I'm the Director of Communications at MEER. We are so glad to be getting together for another MEERTALK, and today we're going to be hearing from Tim Garrett. Then we'll take questions from Dr. Ye Tao and from the community at large. So I wanted to mention that MEER has deployed 700 sensors in the Freetown area, and we're beginning this larger experiment. So if you would like to contribute toward our efforts to cool the planet, we so appreciate your donations. You can go to meer.org/donate. And thank you to those of you who are contributing. You could also write to info@meer.org if you'd like to be in touch. So let me tell you about our guest speaker today. Tim Garrett is a professor of atmospheric sciences at the University of Utah. His research interests focus on the measurement and modeling of clouds and precipitation and their role in weather and climate. And you can read a lot more about him online. He has an extensive bio. If anybody has questions that come up while Tim is presenting, you can send them along to the co-host Barbara in the chat. Okay, Tim, well, we're so glad that you've been able to come here today, and we'd love to hear what you have to say.
Oh, thank you very much for the invitation. It's a pleasure to be here. So the question I want to address today is, are clouds a dial we can control to mitigate climate change? And there's a lot of talk about modifying clouds in one way or another. I have some concerns about this, and I'd like to sort of present some ideas I've been going through about whether or not this is, in fact, something that we can reasonably expect to control. So let's start off by just showing some pretty pictures of clouds, because I think clouds are pretty, maybe underappreciated. There's a lot going on in clouds, and they're kind of complicated creatures, and as a physicist, I like to think about how they actually work, but I also don't like to lose track of the fact that these are rather beautiful. Here's a little puffy cumulus clouds and the stages of evaporating with some cirrocumulus ahead, above them, and here's some more cumulus clouds at a sunset, rather beautiful, over the ocean. Mammatus clouds, these are one of my favorite, these undulating balls of condensation that hang from underneath clouds and actually remain largely a mystery as to how they form, although I have some ideas about how this works. They're quite exquisite to look at sunsets, particularly in summer. Here's some altocumulus. Notice here that we have bright bands and clear bands between the clouds. It's kind of beautiful. But then here we also have clouds that are very solid decks, these stratus clouds that make for gloomy skies, particularly in the Pacific Northwest. Much more complicated scenes. This is a photo taken from a field program I was part of, where one of NASA's airplanes that I had an instrument on, the ER-2, which was like the W-2 spy plane, which, oh, no, not the ER-2, sorry, it was a B-57, which was a reconnaissance plane that I put an instrument on that used to fly around nuclear explosions. And they took these wonderful photos from up high of all the complexity of a tropical cloud field here from south of Key West. Here is a real tropical cloud field where there's a massive complexity. I mean, look at everything that's going on here. We have really deep convection, as we would say in our atmospheric sciences parlance, where big cumulus clouds, cumulonimbus clouds, move up towards the tropopause between the troposphere and the stratosphere, and then spread out as these cirrus anvils, these decks, wide decks of clouds. But meanwhile, scattered all around them are these much smaller cumulus clouds hanging around lower down near the ocean, waiting for their chance, possibly, to become a big cumulus cloud. And not all of them will make it. But then we also have these kinds of clouds, which are the clouds that I think perhaps are of more interest to this group, where we are thinking about how clouds can be modified by human activities. And we have some, really clear examples of this. In the top right, we have, of course, contrails, clouds that are produced by jet engines, because, of course, a byproduct of combustion is water vapor. And cold temperatures, the water vapor mixes with the dry air. And due to some interesting physics, it can lead to condensation, as evidenced by these contrails. And then the clouds actually take on their own life and can end up spreading due to another set of rather fascinating physics. Below, we have an example of what's called a punch hole cloud, which is where an airplane flies through an altocumulus deck, and then by lowering the pressure in its wake, it leads to a very rapid cooling that creates a transition between liquid clouds, which are what you see for the most part there, to ice crystals. And then the ice crystals fall, leaving a hole behind. And on the left, we have something called ship tracks. Those lines in these stratocumulus decks over the oceans are those associated with ships that pass underneath these decks. They release large numbers of particles into the atmosphere. This was actually my master's thesis, was studying this physics and figuring out how many particles they release. And I came up with an extraordinary number of 10 to the 16th power per second of particulates are released by these ships burning the most dirty fuel possible, because that's the cheapest. And then these particulates change the properties of clouds in a way that makes the droplets more numerous, smaller, and the clouds consequently brighter in a way that's actually quite visible from space. Interestingly, US military ships do not make the same ship tracks, which is convenient for them, I think, for obvious reasons, because they do not burn bunker fuel, this diesel, very coarse grade diesel fuel with lots of sulfur in it, but rather remarkably, US naval ships burn jet fuel. And so that doesn't lead to the particulates. But in any case, we have these examples of where it seems possible for humans to modify the properties of clouds. And that immediately gets a lot of people thinking about how could it be, is it possible that we could modify clouds in such a way that we could offset global warming? We could somehow make clouds have less of a warming effect for high clouds and more of a cooling effect for low clouds. So here's an example of this, a work that was initially proposed by my colleague at University of Nevada, Reno, Dave Mitchell, where he suggested that if we seed cirrus clouds, we could shift the formation mechanism of ice crystals in cirrus clouds from a mode called homogeneous nucleation, and I don't want to go into the details of that, but one that leads to very small ice crystals, to one of heterogeneous nucleation, which would lead to larger ice crystals. Larger ice crystals fall faster. So if we have large ice crystals that fall faster, we could expect cirrus clouds to be perhaps smaller, less common. And it's largely believed that cirrus clouds have a net warming effect on climate. So by adding these seeds, we could potentially offset the warming of climate from cirrus clouds and lead to a cooler climate. That is the thought. And this is, captured some attention. I was recently at the American Meteorological Society meeting in Baltimore, and there were a significant number of sessions on this idea of cirrus cloud thinning. Another idea is related to these ship tracks. And this other form of, I guess we could call geoengineering, is marine cloud brightening. And here the idea, I'll just read it to you, is that seeding marine stratocumulus clouds with copious quantities of roughly monodispersed submicrometer seawater particles might significantly enhance the cloud droplet number concentration, and thereby the cloud albedo or reflectivity and possibly its longevity. This would produce a cooling. And so the idea here is we got a plentiful supply of particulates in seawater. sea salt could potentially act as a seed for new droplet formation in clouds. And that would produce an effect that's basically analogous to those ship tracks I just mentioned to you, leading to marine cloud brightening and hence a cooling that could potentially, let's say, in the Arctic or the Antarctic, lead to new sea ice formation. So I think these are nice storylines. And what I want to go into now is some concerns I've had actually, kind of throughout my career and increasingly lately, that maybe these effects are, we're accepting these ideas a bit too readily. And what I want to propose here is that when we're talking about global climate change, the key word here is global, not local. Here we have a beautiful picture of our planet taken by the EPIC satellite from the Discover mission. This is a wonderful mission where NASA put imager on the back of a satellite that went to what's called the first Lagrangian point, which is where the gravitational pull of the sun and the earth are equal, is a point that's really very far away from Earth. And so while this satellite was designed to look at the sun, to look at sunspots, on the backside was an instrument that looks at the Earth. And here's an image of the Earth, and it takes a picture every hour and 40 minutes. And you can see the Earth spin beneath it, completely illuminated. So where we only had one blue marble picture at one point from the Apollo missions, now we get one every hour and 40 minutes with the Earth's disk fully illuminated. And we look at this, and I think, you look at this, you see a characteristic picture. This is what we expect the Earth to look like. I mean, a lot of blue, of course, from the ocean, but also these clouds with these characteristic features of swirliness at the mid-latitudes associated with synoptic storm systems, and with deep convection, like I showed you earlier, around the tropics, where clouds get really big and high, and they are generally more narrow. And what my question here is that, yes, maybe we can affect clouds locally, but what is going to be the spin-off effect when we think about global effects, those that we really care about for climate change, at perhaps not just now, but maybe at some later time? What will be the feedback mechanisms that take place with regards to any local perturbation we might enact? And so just to give you a little bit of the overview of my thinking of clouds, is that I'm trying to think about clouds, working with some really wonderful graduate students on spanning the scales, thinking about all the different scales that go on this planet. And, on the lower right, we had this wonderful image, I love this, from the Cassini mission that went to Saturn. And there's a picture of the Earth's as a little pale blue dot, as Carl Sagan famously put it. The pale blue dot of Earth is just this glowing blue orb. And then if we go down to finer scales, we could look at this averaged image on the lower left, which is an averaged image of Earth from one perspective, taken from geostationary satellite images, where we can see, a bright band at the equator with a deep convection, and then we can see another set of bright bands at the mid-latitudes, with darker bands in between, except off the coasts of the western coast of the continents, where we have really big stratocumulus stacks. But then we can go down and look in detail on the upper right in the tropics, and we see vast array of complicated cloud structures. Oh no, the problem's looking really hard now. And then if we go to the even smaller scales, on the upper left, these are the scales of millimeters, where people have used a holographic device to measure clouds from an airplane, and they see structures that almost look like weather systems, but at the scale of droplets. And so one thing we are trying to work with is sort of trying to think about how are the structures of clouds similar at all ranges of scales, from the millimeter scale up to the planetary scale. And we are finding some remarkable simplifications that I think lend us to think that, well, despite the complexities of clouds, maybe they are rather simple. So in that vein, I'd like to talk about two simplicities that I think are in the Earth system that are relevant to the problem of whether or not we can, as humans, modify climate by way of altering clouds. Now, of course, we can modify climate by way of emitting greenhouse gases. That's not the question at all. The question here is merely about clouds. And one of these approaches is going to be the one I'll mention right here that was led by one of the real true leaders in the field, Graham Stevens. And another is some work I'm doing with graduate students. So there's a remarkable result that has shown up recently, which is that the albedo, the reflectivity of Earth, has a remarkable symmetry between the northern hemisphere and the southern hemisphere. And if the Earth was just completely an ocean, you might say, oh, okay, well, that seems pretty normal. I mean, the northern hemisphere is the same as the southern hemisphere, basically, and we have a reflectivity globally average that's the same between the two. But that's not the case on Earth. The case on Earth is that, of course, most of the landmass is in the northern hemisphere. There's much less on the southern hemisphere. Yet, the albedo, the globally average reflectivity of the northern hemisphere and the southern hemisphere end up being almost exactly the same. As is said here in this paper on the albedo of Earth, the cloudiness of the planet is the principal regulatory agent that maintains the symmetry, with the increased energy reflected from southern hemisphere clouds precisely balancing the larger reflections from northern hemisphere land masses. Somehow, the Earth is managing to figure it out so it reflects equally in the northern hemisphere and southern hemisphere. And we have actually enough data now from satellite observations to look at whether or not there is a trend in this. And what we notice is that actually the global albedo of the planet is actually dropping for reasons we don't understand yet. Yet this symmetry is remaining. It is not changing. So that's an intriguing thing. And then I think there's another aspect here too, which is that if we look at this Earth, looking at the same picture, I want you to just look at the cloud sizes on this image. And I think you might notice something perhaps really quite apparent, which is that there's a lot of small clouds here. Far more small clouds than there are large clouds. We've got these little specks flecking the planet, and then these really large continuous streams of clouds. And this is sort of a general principle that we see throughout nature. Everywhere we look, we see a small number of big things and a large number of small things. And these are in particular proportions that we see not only in nature, but also in human society. For example, the frequency and intensity of wars, very small number of big wars, large number of small wars. That has a particular functional relationship that is the same as the functional relationship that determines the frequency of words in any book you read, in any language. It's called Zipf's law, which is that we have a very large number of words like the, and a very small number of very complicated words. So the same thing we see actually for clouds. And this is a paper that I did with my graduate student, now a PhD student. This was his master's thesis, where we wrote a paper that came out just in January, where we looked at the size distributions of clouds. What is the relative frequency of big and small clouds? And we found that in satellite data, the mathematical function describing cloud sizes, what is called a power law for what it's worth, is remarkably robust to latitude, season, and land-ocean contrasts. So it doesn't matter where we look, we get the same result. Statistically speaking, cloud perimeter distributions, which was the quantity we looked at, the edges of clouds, was more determined than atmospheric stability, than Coriolis forces, the fact that the Earth spins, and that spinniness gets more pronounced the further north or south we get. Surface temperature, didn't matter what season we looked at. Or perhaps a key thing here for thinking about anthropogenic changes, aerosol loading between continental and marine environments. We saw no difference between the ocean and the land. So to get, I've got the data here, and this is my study. I'll go over this, and I don't want to spend too much time on this because these are somewhat mathematical plots. But to give you an idea here, that here on this left side, we have the counts of clouds, the numbers of clouds we measured, and these are their sizes measured through the quantity of the perimeter. And I looked at the perimeter for particular reasons related to the energy exchanges, but just it's the size of the clouds. And then we could see there's a large number of small clouds and a small number of large clouds. And we do this on a log-log plot because we expect this to be a straight line on a log-log plot. These are all the different data sets we looked at, tons of different data sets from satellite data sets. These curves are offset, so they would all lie on top of each other if we didn't displace them. And so you could imagine, if you just remember back to basic mathematics, that we could have a slope for this curve. That slope is an exponent in power law. Doesn't matter. The slope has a particular value. We gave it the symbol beta. And that value beta, that slope, has a value of 1.26. So I just want you to keep that number in mind. We have a value of 1.26 for these clouds. If we look at the seasons, northern latitudes and southern latitudes, whatever season we look at, which is a bit like the temperature, isn't it? That slope does not change. We have a constant distribution for those clouds. The clouds are effectively not changing in their relative sizes, whatever the complexity is that goes on. I go look at different latitudes. Mid-latitudes, tropics, southern mid-latitudes. The tropics have totally different clouds, remember, than the mid-latitudes. That's what we're used to thinking of. We don't have deep convective clouds at mid-latitudes like we do in the tropics. Yet, that slope is the same. And if we look at surface type, land versus ocean, the land is polluted. The ocean is clean. The land has different types of clouds than the ocean. Nonetheless, the relative sizes of clouds is determined by a relationship that is the same relationship we see everywhere. Now, there's a difference between a theory I came up with. I expected a slightly different result. And for a long time, we're trying to wrap our minds around why theory didn't agree with the models and the observations. And eventually, I think we realized that it's a matter of perspective. If we look down from space, we are actually looking at clouds from a different perspective than we would if we were looking within the atmosphere, within layers. So why it's a difference of 1.26, we're not sure yet, but we have some ideas, and we'll look at that later. In any case, the main message I want to give is that at global scales, symmetries abound, that whatever the complexity of clouds is, the albedo or the reflection seems to behave very simply, and the cloud sizes behaving very simply, despite clouds being extraordinarily complex in the here and now. Something rather beautiful is underlying cloud behaviors. Somehow they know how to behave at a global scale. So I'd like to come back to ship tracks here as a possible explanation or thought about what might be going on. So let's look at these ship tracks. These are those brighter clouds that are created when a ship passes underneath, and it creates this change in the cloud properties that shows up in these lines where the clouds become much brighter than the surrounding clouds. And, this is because they release the particulates into the clouds, and that changes the properties of the clouds. It's not the particulates themselves, but what happens to the clouds as a consequence. And you look at this, and I think you would say, well, no, come on, clearly. Adding pollution changes the properties of clouds and makes them brighter. This is inarguable. And I would counter, well, hold on. Let's look a little more carefully. If you look at this line right here, do you notice that there's a dark band on either side? It's bright in the middle, but it's darker than the background on either side of it. And I think our eyes are naturally drawn to the bright part, ignoring the dark part. Some of that dark part going on right here, down here, 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 here. So isn't that interesting? Now, what might be going on there? And I think what is happening is that somehow the perturbation to the cloud is creating a circulation. So you can imagine the ship creates a ship track, that bright band, but then there is a circulation that is created somehow by some mechanism, and there are various possible theories that are out there for what might be going on, such that there is necessarily an ascent here that creates really bright clouds here with necessarily a compensating descent on either side. What goes up must come down. There's only a certain amount of air to go around. The air can't keep going up, so it comes down. And that is what creates the dark band on either side. As the air coming down, clouds cannot form in subsiding airs that's moving downwards. So, this is why I put up this cartoon. Look, Mooch, there's not a cloud in the sky. Well, where are they? Is that we have where it's dark or clear, there must be a cloud somewhere else. There's a certain amount of cloud to go around associating with rising motions that must have compensating subsiding motions. And here, this is writ on a larger scale, where here we look at our basic understanding of how the tropics work, which is we have moist, cloudy ascent with these really deep convective clouds with the cirrus anvils up high. Air is rising, but there must be a compensating descent on either side. And I was just reviewing a paper which was making the argument that, for example, if these clouds get deeper here, they are going to cool the surface. If they cool the surface, then it turns out we get more inflow right here, and the clouds get even deeper, and there's more descent on either side. How do they cool the surface? Well, they cool the surface both by precipitation, but also by blocking out the sun. If the clouds shrink, it's called iris shrinkage. If they shrink, yes, they get deeper locally, but they let in more sunlight elsewhere as a compensating effect. And there's more subsidence elsewhere, so there's less cloud elsewhere. So, and I did this at the tropical scale just to go on and say that this happens at the global scale too. This is like the most basic plot of the Earth, which shows for the red line, the absorbed solar radiation from the Earth, which reflects the albedo aspect, the reflectivity of the planet. If the reflectivity of the planet goes up, then this curve must go down. This is latitude. This is the energy. Notice that it's a bit of this characteristic curve right here reflects the fact merely that the Earth is round. We've got less that's absorbed at the poles, more at the equators. But how much the Earth emits to space is this other curve. This is a long wave emission to space, thermal emission to space, how the Earth cools. And there's a difference between the two, which means that if we subtract this one from that one, then that means that we have more coming in of energy than we have going out. And that is this surplus right here of energy, whereas at the poles we have the deficit. Now, this is your basic atmospheric sciences lesson, I'm sorry. But the main thing here is that we have this global phenomenon that goes on that we will always have to speak to, which is that there's absorption at the equator, there's loss of energy at the poles, and then as a result, because there's absorption, the Earth heats up, there's a rising motion at the equator, there's a compensating sinking of the motion at the poles. So if we create a local effect, we have to put it within this global context of the general circulation of rising and sinking, where rising leads to cloudiness and sinking leads to reduction of cloudiness. So, basic message here. To borrow a line, what happens in Vegas doesn't stay in Vegas, but we're doing this for atmospheric sciences and for cloud production. That clouds share energy and air at global scales. And when we look at the planet, we see some underlying simplicities, like some really interesting fundamental underlying simplicities that I think we as a community in the atmospheric sciences are actually struggling to fully understand, although we do have some ideas of what's going on. But nonetheless, the size and the reflectivity at the global scales that matter for climate change seem to be constrained. And the reason why this happens is because, again, we're all sharing energy and air. If one gets more than somewhere else, there must be less. What goes up must come down. More cloud here almost necessarily means less cloud later and elsewhere. So, you can have a good time in Vegas, but there's going to be a hangover later and when you get back home. So keep that in mind. All right. Well, thanks. I'll be happy to take any questions if you have any.
All right, great. Well, we are actually going to bring on Dr. Ye Tao to speak with you and ask you a few questions. And just a reminder to everybody that you can send your own questions to co-host Barbara in the chat. Dr. Ye Tao is the founder and director of Mirrors for Earth's Energy Rebalancing. He received a doctorate from the Department of Chemistry at MIT in 2015 and completed research requirements for a doctorate in physics at ETH Zurich. He led a research lab at Roland Institute at Harvard, as you may know, and left to devote himself to the singular task of bold and creative engineering solutions and helping with this problem of heat on the planet. So, Dr. Tao, I'm glad you have time to be with us today.
Thank you, Kaisa. And thanks for team for joining us and illuminating us on these upper level constraints, of which I'm a huge fan of. Like in our own work, we also looked at what the systematic constraints on energy and the implications of that for the efficiency of any climate cooling technologies that they must have. And many questions, I'm sure we won't have time to go through all of them. And the talk just inspired many more. Some are very simple. Can you maybe bring up the image of the cloud track? So I guess my question is like on whether there's an alternative mechanism or mechanisms explaining the depletion of brightness or clouds from the periphery of the brighter ones. Could there be like 3D radiation effects, meaning that let's say the sun is coming from a certain direction, it's projecting shadow, thus the shadow is on the side of the clouds. Is there evidence for preferential formation of the dark track on one side of the clouds? Have you noticed it?
I actually, it's an interesting thought. I never thought about that. But I mean, it is a topic of research, is 3D effects by clouds. I think rather because we're talking about ascent and descent, that at least for this argument, that the predominant theory is that in ship tracks, there's less precipitation. Because the cloud droplets get smaller, they are less likely to combine and coalesce to form bigger raindrops. With bigger raindrops, there's less precipitation. And with less precipitation, there's less evaporative cooling below cloud base. And then that leads to a dynamic response that leads to a circulation. That's a dominant explanation. It's not my favorite explanation. My favorite explanation relates to if the droplets get smaller, it turns out that clouds are more efficient at radiating thermal energy to space. So there's a property called the emissivity of a cloud. I don't know if your work in Sierra Leone thinks about the emissivity of metal plates at the tops of buildings, because metal, of course, has a very low emissivity, and if it's rusty, it has a very high emissivity. But clouds have, a property called an emissivity, which is the efficiency at which it emits to space. The droplets get smaller, it's more efficient at emitting to space, which creates more cooling at cloud top. With more cooling, then that creates also a dynamic circulation of the type I mentioned.
But wouldn't the cooling, for example, create a subsidence and actually dropping of the basically the inverse of what you depicted?
Yes, but the atmosphere already has rising motions in the center. So the preferential thing is if there's cooling, there's two things that can happen. One is that you can have sinking, and the other is you can have spreading, that actually you have something called a density current, which is that if air is colder than its surroundings, what will happen is that it will slide out sideways, and then the warm air will slide in to replace it. And so that is the circulation I'm thinking of. And at one point, I had the project to actually put this into a numerical model and try to simulate this directly. So it's really nothing more than a mental model for what goes on. But I did do some work where I actually looked at how this phenomenon goes on in the Arctic and actually measured in the Arctic, or it turned out that pollution that came from mid-latitudes that went into the Arctic ended up making the clouds much more efficient emitters of long-wave radiation, both up and down, in a way that had a warming effect on the Arctic surface. So we measured this effect, and we know that this is, real physics. How it plays out dynamically for ship track is not something I've actually explored, and I'm not aware that others have explored either, but I suspect that this is really what's causing this effect.
Okay, great. Thanks for that. And the log distribution, the straight line that you mentioned, that's a probability density. But what about the normalization factor? I mean, the curve has certain shape, but what about the total number? And that
Yes.
seems to be fluctuating with seasons, right? So somehow you can control that.
Well, I didn't show how it could fluctuate with seasons because but yes, you're right that of course the total amount of cloud fluctuates with seasons. So I was only talking about the relative numbers of clouds. However, what I showed there was testing a theory, only one component of the theory that I developed in a paper that was in 2018, and I was actually continuing to work on this morning from another perspective. And in this theory, the only ingredient that's a tunable item for determining the total number of clouds ends up being the stability of the atmosphere. And so for those who aren't familiar with what stability of the atmosphere means, if the atmosphere is unstable, then what it means is that the way the air is stacked is such that the atmosphere wants to turn over if it's unstable, and that's when we get the really big thunderclouds. And if it's very stable, we might get no clouds, or at the most, sort of these very stratiform clouds, the stratocumulus decks or stratus-decks. That gray picture I showed you of a gray sky earlier in the talk. So it turns out that the amount of cloud, the key ingredient, at least how I see it, is the stability. And there are some other people who are, from another perspectives, are starting to see this. They're saying that, hey, wait a sec, hold on. Where we are arguing that we can inject aerosols into the atmosphere and change the properties of clouds, there may really, all you are measuring is the amount of instability in the atmosphere, or stability in the atmosphere. So for example, not to go into too much depth, but when we get the biggest cumulonimbus clouds, it's in the least stable environments, except you have to have a very stable bottom atmosphere in order to get the cumulonimbus to trigger. So we talk about convective available potential energy. That's where the cumulus clouds get really big, but also convective inhibition, which is in the boundary layer where there's really stable. And there the atmosphere is building up energy, and it's like a pressure cooker. If we have a strong lid on the pressure cooker, then it can build up a much higher level of energy before it eventually gets released. Well, it turns out if the atmosphere is really stable down below, then the aerosol concentrations are really high. And we end up with this false relationship between high aerosol concentrations and really big, deep clouds. So what a lot of people are now saying is that, look, it's probably just the stability that determines how the clouds behave. And I would say for theoretical reasons and observational reasons that I agree. That the aerosols don't really have a role to play, because ultimately the clouds have one role in life. And their one role in life is to take too much energy, mostly from the sun, that's down below, and move it up high, where it can be radiated to space. That's why we have clouds, or why Earth is so special and how efficient it is at doing this mechanism. Clouds exist to take energy below and move it up high, where it can be radiated to space. And I don't see ultimately a role for humans to control that, because that role of clouds is one that's determined by a global energy balance.
All right, I really like the analogy of the pressure cooker and there's some sort of activation energy that's required to overcome a certain natural stability. And that really reminds me of the concept in chemistry of activation energy for a reaction.
Same thing. Absolutely.
Right, but in that case, we have things called enzymes and catalysts. some of which are artificial that enables
Okay.
you
Yes.
to overcome.
These are wonderful examples, and these are the same sorts of thinkings I have. Yes, yes. So you could have basically an enzyme that increases the efficiency of creating a cloud, and aerosols could actually do that. But if you think about it, let's say the aerosols did make, well, let's say it was an enzyme that managed to make a reaction happen faster here, then that chemical reaction is consuming all the available energy here, needs less available for a similar reaction elsewhere. And when the total amount of energy is globally constrained by this balance between solar energy input and thermal output, they all have to share. Maybe one, for whatever reasons, consumes more here. That's going to mean less available to consume elsewhere. And ultimately, through this competition, you end up with that mathematical distribution that I showed, the power law, that with the slopes being something that, there's maybe a universal principle without the atmosphere, because it seemed that same degree of sharing wherever we look with the same mathematical relationship.
I'm completely in agreement with this total energy constraint. What I'm curious is, because different type of clouds probably do not dissipate energy at the same power density per unit area. And we're talking about the planetary energy balance. It's a surface phenomenon rather than 3D phenomenon in which the clouds are evolving. So my question is, if we can artificially, design cloud forming catalysts over the surface by surface heterogeneity, such that very small instabilities leads to just enough convection and lifting to form really low level cumulus clouds, which are, for example, the best ones, for controlling the warming aspect of things. Is that compatible with your understanding?
Okay, so if you're asking whether or not you could have a local effect, I mean, could
rather I'm asking whether we can locally utilize the available energy that's coming from the sun to locally produce low-level clouds that do not deplete the total available energy too much in a single go in the tropics, for example, in this, I don't know the terminology, but really high cumulonimbus clouds, but rather just form a whole bunch of really low-level clouds. Is that compatible with the energy constraint?
So I think so, yes. At a very local level, it must be possible to create clouds that are distinctive for that location. I mean, we know that's the case because we see particular clouds associated with mountain ranges. Or I think perhaps one of the best examples is that there is a cloud that has a name. And you think, well, clouds are constantly coming and going. But no, there's actually a particular cloud that has a name on Earth. It's called Hector. And Hector is this cloud that lives on the Tiwi Islands north of Darwin, Australia. And Hector got its name because around in the early afternoon, it is the biggest, deepest cloud in the world. And it just shows up every afternoon. Hector reliably shows up and creates this cloud, maybe 20 kilometers tall. It's a magnificent cloud. I've seen videos of it forming, and it just looks like a nuclear explosion. And it got its name during World War II because it was actually used as a navigation mark for pilots. There's Hector. Well, now we know where we are. We're near the Tiwi Islands. So Hector forms because presumably the Tiwi Islands are just the right size and shape, and they are embedded in this what's called the tropical warm pool. There's these very warm oceans, such that the conditions are just right to produce this really big cloud. So, I mean, I think these are just examples, but they're examples of how it is possible to locally see changes in, say, land configuration one way or another that do produce particular clouds that we can reliably count on. A lot of people are looking at, for example, they do modeling studies where they'll create grids of, let's say, crops in particular grid structures where the different crops are arranged in such a way that they might lead to more clouds of one type versus another. Certainly, how the land looks changes what clouds show up above them locally. But we have to accept that there is this phenomenon, people talk about it in cloud seeding. It's something probably my PhD advisor had actually coined, which is that we were robbing Peter to pay Paul. And that what happens in one place necessarily means less of the same thing elsewhere.
Thank you so much for the discussion. I could go on, but I think I should leave the chance to others to ask a few questions. Thank you very much.
Thank you.
Okay, thank you, Dr. Tao. We do have some questions that have come in. First of all, Mana would like to have some clarification. People seem to confuse chemtrails, I assume chemical trails, which are in the troposphere, with SAI, stratospheric aerosol injection. So could you help to clarify about which levels these are in, that kind of thing?
Well, chemtrails are a fiction, but there's contrails, and contrails are, condensation, because we burn fossil fuels and jets, and that leads to the principal byproducts of carbon dioxide and water vapor, and the water vapor condenses to create condensation, but it's condensation of water to create a cloud. And clouds are made of condensed water, liquid or ice crystals. In this case, it would be ice crystals because the planes have to fly quite high before the contrails show up. Now, as for stratospheric aerosol injection, that is another form of geoengineering that is very different. There we're talking about, we're not expecting condensation to happen in the stratosphere. The stratosphere is much too dry for there to be any appreciable level of contrail production. And planes don't fly that high anyway. But we could put aerosols into the stratosphere, sulfur aerosols, I should put them on a rocket, and then explode the rocket to produce basically a mini volcano in the stratosphere, do it continuously. And because those aerosols are up there in the stratosphere, and the stratosphere is a very stable environment, once it's up there, those aerosols can last for a very long time. And we know from the not so long ago Pinatubo eruption that the Pinatubo sunsets lasted for a couple of years. It was a long-lasting effect. I mean, eruption was momentary, but the aerosol stayed for a very long time. So those are very different. Those are aerosol particles, sulfur aerosol particles, that, like any particulate, they reflect sunlight. And that could be a form of geoengineering that at one level would work, because it would block out sunlight. And on the other other hand, it could have all sorts of foreseen and unforeseen negative consequences. I mean, if nothing else, blue skies would be much less blue. But I don't know what it would do to photosynthesis or global weather patterns. But it would block out sunlight. Contrails, I think, my feeling that if you have contrail formation here, that means less cloud formation elsewhere. I think the same principles would apply for the contrail formation. Stratospheric aerosols, I think that's a different argument.
Okay. We have a question from Jeff. Because you talked about cloud seeding, what types of vegetation seed clouds the best?
Well, normally what we would do for cloud seeding is the characteristic substance that is used to seed clouds is a substance called silver iodide. It turns out that silver iodide is it's just a chemical, but it has a rather special physical structure of the bonds for silver iodide that almost exactly mimics the structure of frozen ice. And because it mimics the structure of frozen ice, essentially the silver iodide tricks droplets that are very, very cold, well below the freezing temperature, but haven't yet, as I mentioned, homogeneously froze. they trick it into freezing by coming in contact with that supercooled, is the word we use, supercooled droplet. And then the droplet says, oh, hey, I got something that looks like ice here. I'm going to become ice. So that is the substance that is typically used for cloud seeding. However, it turns out that biological agents can be actually even more efficient. They're just more difficult to come by. And there's a lot of work that's gone into showing that even things like leaf litter can be a very effective at overcoming, as Professor Tao said, that going from overcoming the activation energy to go from a liquid phase to an ice phase. And that's the key ingredient there, is just to have something that will enable to do it. Biological agents can do it too. You just can't manufacture them as easily.
Mm-hmm. Okay, here's a question from Eric. How do the longevity of the ship track clouds compare to other clouds? More generally, can you speak to how the longevity of clouds differ and how that might affect the radiation balance of the Earth?
Well, that ends up being a very philosophical question, because in order to define the longevity of a cloud, we have to define what a cloud is. And in that regard, clouds are constantly forming, dissipating, and reforming again. So when you look at a cloud, you could look at this cloud and think of it as being this static agency. And really, that's just a reflection of your attention span being much shorter than the actual time it takes for air to move through the clouds. And if you actually put yourself through the mental exercise of, maybe with a beer in hand, just sitting there on the porch and trying to force yourself to watch a cloud over about 10 minutes, which is the time it takes for air to move through a cloud characteristically, you would see that it's not really even the same cloud anymore. It's actually may look sort of like the same thing, but it's gone through some sort of life cycle of about 10 minutes. Now, nonetheless, I could see where you're coming through with the ship tracks. And the ship tracks look like they are these long lines. They're hundreds of kilometers long, 10 kilometers wide, maybe 20 kilometers wide. These look like real features that are, long-lived. The ship's not moving at 200 kilometers an hour. Yeah, they're hundreds of kilometers long. So obviously these things are lasting for, maybe even a day. But I want to create the distinction here that these clouds, like us, take on a life of their own. We are constantly regenerating ourselves on a daily basis through the consumption of food. These clouds are doing the same thing. They are constantly regenerating themselves with, at a time scale of about 10 minutes. It's a buoyancy period of moving up and down. So how long does a cloud last? What affects its longevity? I would agree that they do last a very long time. And I think the reason is that the clouds, because ship tracks, for the reason I mentioned, they emit thermal radiation to space very efficiently. Because they emit thermal radiation to space more efficiently than the surrounding clouds, that creates a circulation. Because there's a circulation, there is a return updraft that again recreates the cloud and then sustains the cloud through the air, moving up and down and up and down and up and down. And there's nothing really to stop that until perhaps some other weather pattern comes through and tears it apart. But in the meantime, it can last a while, just like us. We constantly recreate ourselves and reform because we can.
Right. Here's a question from Louise. Are there international or even national regulations about who can cloud seed? What are the regulations about these sorts of things?
Yeah, I don't think for cloud seeding, I'm not aware of any for cloud seeding. And one reason it might be is that, at least for cloud seeding for the production of precipitation, In my field, atmospheric scientists have largely doubt that it works at all. And I think what it comes down to is that, as I mentioned, a cloud has to happen to satisfy this issue that the atmosphere is unstable. If there's instability and there's loss of cloud production, then there will be rain. But what determines whether or not there's rain is the instability. We could add aerosols to it, but it's not clear, or it's been very difficult to show conclusively that anything really conclusively happens. And part of the reason is this phrase I mentioned, robbing Peter to pay Paul. Even if we produce more locally here, there's probably going to be less moisture that is condensed and precipitated out elsewhere.
Mm-hmm.
I'm not familiar with any regulations. Perhaps there are somewhere. I know I know my own state of Utah just increased by a factor of 10 its investment in cloud seeding. So it is one of these, I think, a fable, but a very persistent fable that I wish the state of Utah gave those millions of dollars to my research rather than to something I don't think works.
Indeed. Okay, here's maybe just a question or two, if that's okay, more if you have time. We have a question from Peter. What are your thoughts on what would happen if the Arctic, the ice was to retreat, like a blue ocean event? And perhaps you suggest that the ice may be replaced by low cloud, which would lessen the impact of, low cloud formation, lessening the impact of the ice disappearance. Or
yes. So
maybe,
I think that's a really
what's your opinion on all of that?
Yeah, so I mean, my opinion is that sea ice is a low-flying cloud. Sea ice is white, clouds are white. From the physics perspective of thinking about, we talk about radiative transfer in the atmosphere, how sunlight moves through objects. The reason that sea ice is white and clouds are white are the same, is that you have little particles, snow particles on the ground or droplets in the sky that are spatially separated, and then light bounces around. And then it comes back out and is white. From the perspective of the planet and the radiation balance of the planet, well, I mean, whether it's down on the ground or a kilometer up doesn't really matter. And so I think what we are seeing, there's a lot of argument that what is happening is that as the sea ice retreats, of course, the exposure of the atmosphere to the, I mean, not warm, but I mean, the warm, relatively warm ocean compared to the air, exposure to all this moisture and energy, of course, creates the potential for more cloud formation. And so what we are merely doing is shifting that sea ice to use physics words, to a higher energy state. We're moving it from near the surface up above. But the end result is perhaps, in terms of the effect on the Arctic, mutant. So the argument that was very popular for a long time was that there would be a sea ice albedo positive feedback, that as the ice retreats, the sunlight comes in, warms the Arctic, and that's an amplifying effect on climate change because lose sea ice and more sunlight's absorbed, lower albedo, more absorption, warmer planet. And I think in terms of the Arctic, we're now having a more sophisticated view that perhaps that's not quite true.
Well, we have one more question, I think, and then I had a question for you too, just to close things up. But let me just see here. It's about, you had mentioned about marine cloud brightening, and do you think it's even feasible to cool the Earth at a global scale or a regional scale with marine cloud brightening?
Myself, no.
Whether or not you agree with it, or
So I just caution, my views on a lot of these topics are a bit of a minority in my field. I think my colleagues who I mentioned them to sort of kind of begrudgingly agree that maybe I'm right, but I, let me just put it this way. As proper scientists, I think it's important to set up what the null hypothesis is. And then we assume that the null hypothesis is the case until proven otherwise. And I think the null hypothesis in this case has been typically assumed that something like marine cloud brightening will make a difference. Well, I would say really the null hypothesis should be that it doesn't. And that we need to show that it's incumbent on us as atmospheric scientists, the professionals who are, whose task it is to look at this thing, to really make a cohesive argument that local effects on clouds can have a global impact without compensating feedbacks that just remove them to zero, as I would intuitively expect them to be. Currently, the tools we are using to address this problem are global climate models. But global climate models have grid boxes. They're arranged in chunks, discrete chunks, and they model what goes on globally, but using a discretized element that's about 100 kilometers on a side. The most advanced ones are getting up to a kilometer on a side for very special applications. But even then, you look at what's going on. What's the dimension of, let's say, a ship track? Maybe 10 kilometers. What's the dimension of the interactions with the pollution with the clouds? Well, that's on the scale of, millimeters or less. We're never going to be able to resolve those. And I suspect that any study that shows that there is a global impact associated with something like marine cloud brightening is merely only reporting model error. But that's just my a view. Probably just to take it to my colleagues that they're not being as scientific as they should.
Okay, well, I found myself at the very beginning of your talk as you were showing these incredibly beautiful photos of such a variety of clouds. My mind meandered to, as a child, did you find yourself looking at the clouds a lot? Is this kind of was something seeded in your childhood around your studies of
No,
cloud
I
formation?
wish I could say stuff like that. We get graduate student applications for our department, and they all have these wonderful stories about how they saw some meteorological phenomenon and it just changed their life, and all they wanted to do was do vector calculus in undergrad. And of course, they don't want to do that. They just want to look at pretty clouds and storms and things like that. No, I did a physics degree, and then I wanted to do, I don't know, something that was a bit more tangible for a PhD and master's. And so I went into atmospheric sciences and entered a group that was actually one of the leading groups for actually studying clouds, but I did not ahead of time have an appreciation for that. However, there was somebody in that group who I will say kindled my interest. So there was a graduate student, my PhD advisor, his name was Peter Hobbs, and I was a graduate student way back then, who basically flunked out within a few months of graduate school, but kept on working for this, for Peter Hobbs. He was a relief pitcher for the Mariners, and he did TV meteorological broadcasting. And if you look for a cloud chart, it is very likely that the cloud chart, as Art Rangno's cloud chart, is these beautiful square pictures of clouds that he took pictures of. And I remember being on a plane with him where we had a bubble window on the top of the fuselage, and he would stand on a stool in the middle of the plane with his head sticking out the top of the plane, looking at a cloud we would fly into. And he would just look at the cloud and describe everything about it. I mean, you name the cloud, but then go down to describing how many ice crystals there would be and what concentration of what size and what type, what droplets. Somehow, this marvelous intuitive knowledge from all of his experience of studying clouds in this group, so that he could just look at them and get this beautiful story of what was there. And then, of course, we'd fly into the cloud with hundreds of thousands of dollars of the most sophisticated instruments dedicated to this purpose, and, just see exactly what Art had described. And so that always captured me as being an example of how important it is, whatever the theory we have, to just look outside, look at clouds, get that beer, sit on the porch, and just look at that cloud for a continuous period of 10 minutes. It's hard, actually, but there is so much that can be learned just from looking. And for me, that's always I've always been captivated by looking at those dynamics of what goes on. It's something that's really quite beautiful.
Well, that's a really lovely note to end on. I think we all know what we need to do. So we want to thank you so much for coming and really educating us about a very complex topic. Thank you, Tim.
Thank you very much.
At MEER, we're working to help educate the public while also developing a solution to the warming on the planet. We invite you to keep learning about Earth's energy imbalance and climate science on our website. We're an almost 100% volunteer staff, so please consider making a monthly donation of any amount if you've enjoyed being here. And you can check us out on our YouTube channel. And also I wanted to mention that our next MEERTALK will be on Sunday, April 7th, when we'll have Philippe Ram as our guest speaker speaking about climatic architecture. So until then, we hope you will have a wonderful month, and thanks again for coming.